Hi everyone, in this video we are going to talk about sections 9.9 and 9.10. So this is going to be about cells that are under non-standard conditions, and then electrolysis and what we call Faraday's law. This is our last Edpuzzle. This will be the last of our content, so that is exciting. Alright, so our first slide here talks about standard conditions. So if we're under standard conditions, we know that the concentrations of everything is 1 molar, partial pressures of everything is 1 atmosphere, and then we are at 25 degrees Celsius. So if I thought about the Q, a QC or a QP, the reaction quotient here, it's always going to be 1 under standard conditions, because if everything is 1 molar, 1 divided by 1 is going to be 1. Now if we look at this next slide, it's going to talk about when we're under non-standard conditions. So standard conditions only last for a really, really small amount of time, like at the very beginning of your reaction, because once the reaction starts, some reactants are going to go into products and some products are going to be made. So that's going to change the concentrations. So under non-standard conditions, we are not at 1 molar, or we're not at 1 atmosphere, and our temperature could potentially be at a different temperature as well. So again, that's because the reaction is going to go forward, so our concentration of reactants is going to go down, the concentration of products is going to go down, and what that's going to do is that's going to decrease the cell potential or the voltage. So your voltage is going to decrease. And as that happens, once you get to each cell being 0 to 0 volts, that means your cell is dead. Or you can think about it like a battery. That means your battery is no longer working. So when we are under non-standard conditions, we can think about the equilibrium here. So equilibrium for this reaction is going to lie far to the right. They lie far to the right for all voltaic cells. They go to lots and lots of products. They're going to go to completion. So that KEQ is much, much bigger than 1. So our cell potential decreases as we go forward because we're using up that battery. We're using up the energy that it has. So as our reactants turn into products, and as the system approaches equilibrium, or when our Q approaches our K, that voltage is going to go down. Once we get to equilibrium, that is also when our voltage is 0. When our voltage is 0, we're at equilibrium. Again, we're dead. Cell is dead. All right. So sometimes we can change how the battery is working or how the cell is functioning by things like Le Chatelier's principle. So if I add some Cu2 plus to the system under standard conditions, remember our equilibrium is going far to the right. We're making lots and lots of products. That's what it always is for voltaic cells. If I am adding some Cu2 plus, that's going to make it go this way even faster. It's going to increase the rate of the reaction. That's going to give me a Cu2 plus concentration that is greater than 1. So if I think about my Q down here, that's going to make Q less than 1, or it's going to get further from K. This is going to increase my voltage. My volts are going to go up. Your battery is going to last longer, or the cell is going to be able to run longer. There's more electrons. The flow of electrons is going to increase. So if this goes up, Q goes down. And then that's going to get us further away from K. The battery will last longer. Now the opposite is true if I take some of that Cu2 plus away. If I take some of that Cu2 plus away, now my Cu2 plus concentration has gone down. Q goes up, or Q is getting closer to K. So that means now my voltage is going to decrease. This is when my battery is going to die quicker, or my battery is going to slow down. Because what it's trying to do, if I take away some of that Cu2 plus, I don't have as much reactants to move forward into products. Okay, on this slide, it's going to talk about very similar things, except for now we're changing this Ni2+ concentration. So now we're changing something on the product side. So by adding products, we are actually slowing down the rate of the forward reaction. That says forward. Okay, so if I'm slowing down this rate, that means my Ni2+ concentration is bigger than 1. So this number on the top goes up. That's going to make your Q go up. So Q is greater than 1. So we're closer to K, because K is much, much greater than 1. That's going to decrease my voltage and decrease my current. If we were to take away some of that Ni2+, now this number is lower, so that means my Q is lower. So Q is less than 1 and further away from K. We're further away from equilibrium. So that means we're going to pick up the pace. Our voltage is going to increase and our flow is going to increase, our electron flow. All right, the next couple slides kind of walk through a question. So it says, if Ni2+ and Cu2+ are equal, but they're not equal to 1, what happens to the voltage? So let's say that they're both 0.5. Let's look at the next slide, and it's going to walk us through that K, or that Q expression. So this is our Q1 here, where we would have a 1 molar concentration and a 1 molar concentration, or standard conditions. So Q1 equals 1. If I have Q2 where I have 0.5 molar and 0.5 molar, no, I'm not at standard conditions, but Q is equal to 1, so Q1 is equal to Q2. If our Q doesn't change, if our Q is equal to 1, the voltage stays the same, okay? If Q doesn't change, then the voltage doesn't change. Now, if I have a 0.5 molar and a 0.5 molar solution, my battery is not going to last as long, or the cell will die sooner, but the voltage is not going to change at all. All right, so now this slide says, as a cell approaches equilibrium, the magnitude of the cell potential increases until it reaches 0 at equilibrium where Q equals K. So the magnitude of the cell potential decreases. That means the cell potential is going to go down. E cell is going to go down. It's going to decrease until it gets to 0. If I have any deviations from standard conditions that gives me Q of less than 1, my volts are going to go up. If I have any deviations from standard where my Q is greater than 1, my volts are going to go down. So this is further from equilibrium. This is closer to equilibrium. Deviations from standard condition where Q equals 1, then our voltage stays the same. Okay, V stays the same. Okay, so we have a question here that says a cell originally under standard conditions and functioning according to the equation below runs until the Zn2+ concentration is 1.14 molar. Find the concentration of Au3+. So what we can do is we can find how much the Au3+ has changed by thinking about how much the Zn2+ has changed. So the Zn2+ was originally a 1.0 molar because it was standard conditions. We let it go until it was a 1.14 molar. So that is a change of 0.14 moles of zinc per liter. And then this part right here is a mole ratio. So we can assume that since they react in a 2-to-3 ratio, they are going to change in a 2-to-3 ratio. So this number over here, their answer here, this is how much the Au3+ changed. Okay, so now if the Zn2+ concentration increased, the Au3 plus concentration has to decrease because one thing is being oxidized and one thing is being reduced. So it was at 1 molar, and then we subtract the change. This is my new Au3 plus concentration. This leads us to something called the Nernst equation. So the Nernst equation talks about if I have things at non-standard conditions, how can I find the voltage? So this E over here that everything is set equal to, that is the voltage under non-standard conditions. The one with the little circle, this thingy, that's under standard conditions. So that's like what we would look up in our book and do the subtraction of the reduction potentials, minus RT, where R is 8.314 joules per mole Kelvin, T is temperature in Kelvin, and then we're going to divide that by N. N is the moles of electrons that are transferred. So like if I go from an Ag plus 1 to a solid Ag, that is 1 mole of electrons. If I go from a Cu2 plus to a solid Cu, that is 2 moles of electrons. And then, so that's N, times F. F is this thing that we call Faraday's constant right here. It is on your formula sheet. On your formula sheet, it is written as 96,485. That's what I would like us to use. 96485 coulombs per mole electron. And coulombs, it talks about the charge. Think of Coulomb's law. It's talking about the difference in charge there. So we're going to use this number because that is what is on our formula sheet. We always want to use the numbers that they give us. This number is used quite a bit in stoichiometry problems because it's coulombs per mole of electron. So we'll talk about that again here in a little bit. And then Q is our reaction quotient. All right, so if we look at this equation, we have A plus B yields C. I can write my Q, and then I can write my Nernst equation for that. So if Q is less than 1, that means we have more products than we need. So ln of Q is going to be negative, and that means my voltage, my E, is going to be higher than my standard cell potential. If Q is greater than 1, that means I have more products than what I would need. That's going to give me a positive natural log of Q, so that means that my volts are going to be less than the standard. So let's look at a problem where we have to kind of think about that. All right, so we have this equation here that has 3 moles of Ni2 plus 2 moles of Cr as a solid yields 3 Ni as a solid plus 2 Cr3 plus aqueous. Would the voltage of a cell that operates according to the chemical equation above under standard conditions be greater than, less than, or equal to that of a cell where Ni2 plus is less than 1 and Cr3 plus is greater than 1? Justify your answer. So the first thing that I would think about is that Q. What is that Q going to look like? So this is going to be products over reactants. So Cr3 plus, this does have a coefficient of 2, so we're going to raise that to the second power, over the concentration of Ni2 plus to the third power, again because of that coefficient there. All right, so my Ni2 plus is less than 1. So this number is going to go down from standard conditions. Cr3 plus is greater than 1, so this number is going to go up. So that means my Q is going to be greater than 1. So my number on the top is going to be bigger than 1. My number on the bottom is going to be less than 1. So now think back to this slide. If Q is greater than 1, what does that mean about my cell potential? My cell potential here, this E, is going to be less than what it is at standard conditions. So now down here, that's what it says. This would cause the value of E to be less than because of this equation. Okay. Another way that we could think about explaining that question. We know that Q is equal to 1 under standard conditions. If Cr3 plus is greater than 1 and Ni2 plus is less than 1, we know that Q is greater than 1. Okay? When Q is greater than 1, it's closer to K, meaning we're closer to equilibrium. If you're closer to equilibrium, that means your battery is being used up. We're using some of that energy. So using up the battery. As we get closer to equilibrium, our E is going to go down. We're going to get closer to 0 until that battery dies. So deviations from standard conditions will take the cell closer to equilibrium, then Q equals 1, which will decrease the magnitude of the cell potential, or make E go down. Okay, these next few slides are about concentration cells. So these are about voltaic cells that have the same thing at the anode and at the cathode. So it's got the same species in both spots. If we are at standard conditions, our voltage is 0, but E of the cell will be positive if Q is less than 1. So again, think about what Q means. That's going to be your reactants over your products. What's happening at the anode is going to be what's in our products, or it's products over reactants, I'm sorry. What happens at the anode is going to be our products over our reactants. So the concentration at the anode is less than the concentration at the cathode. So then as the reaction proceeds, the concentration at the anode increases and the concentration at the cathode decreases. So think about something being reduced and something being oxidized. When we get to them being equal, that's when your cell is going to die. Okay. So if we look at this picture, we have nickel as a solid at both the anode and the cathode, and then we have nickel sulfate in solution, and then we have our salt bridge there in the middle. So on the left for this picture is the anode, and we can see that our we're being oxidized here. Oxidation happens at the anode. So our solid is turning into that 2+ and giving off 2 electrons. Those electrons are then going to go through our wire because we always flow from A to C for our electrons. At the cathode side, this Ni2+ in solution is going to pick up those electrons and become a solid. That's the reduction half. Okay, so now let's look at a question here. This wants us to label the anode and identify the direction that the electrons flow in the cell below. Justify your answer. So what we need to think about here is what's happening at the anode and what's happening at the cathode. We know that at the cathode, our reduction is happening because of red cat. Okay, so the reduction is going to be where we have reduction is gain. So this is going to be where we have the 2 electrons being picked up to become the solid nickel. Okay. Now let's think about our Q here. Let me zoom this out a little bit. Our Q is going to be Ni2+ over the Ni2+. Okay, this one is at the anode. This one is at the cathode. This is less than 1 right now. So that means the number on the top is smaller than the number on the bottom. So that means that this one over here, where the Ni2+ concentration is less than 1, since that's on the top of my equation, this side is going to be my anode. So we need to get Q to 1. That's when the reaction is going to stop. That's when our battery dies. So what needs to happen, since this Ni2+ concentration is smaller, we need to make it higher. So this is going to be where the Ni as a solid is going to lose those electrons or be oxidized. So the oxidation happens at the anode. So because this concentration is smaller than this concentration, and we know that our Q is less than 1, the anode has to be the one on the right here. Which way do electrons flow? They always flow from A to C. So your electrons are going to go from the right to the left in this equation, or in this instance. All right, so this is just going to talk about that. It's just going through all of that stuff. So deviations from standard conditions where Q is less than 1 will increase our cell potential. So when Q is less than 1, the anode concentration is less than the cathode concentration. Then as we proceed, that anode's going to increase until we get to this point, and then we're at equilibrium. And then we always go from A to C. All right, we're going to shift gears a little bit here now and talk about electric current. So this equation on here is on your formula sheet. I believe there's something that looks very similar to this right here on your formula sheet, which I think is really helpful for this. So electric current is the amount of charge that passes through a cross-sectional area of a medium per second. So it's wanting to know how many electrons, or what is the charge that is going through a wire, essentially. So I is your current, and that's in what we call amperes, or A. Q is your charge, that's going to be in coulombs, and then T is time, and that's going to be in seconds. So anytime we see something that's in amperes, it'll say amps, or it'll say A. We're going to think of that as coulombs per second because of this equation. Coulombs are the charge on the top divided by the time. That's amps. And then we see this Faraday's constant down here again. This is used a lot in stoichiometry because it has the coulombs per moles of electrons. So we could use it just like this, or we could invert it and put moles of electrons on top and the 96485 coulombs on the bottom, which we're going to see here in a few minutes. All right, so let's look at an equation. All of these equations, all of these problems are essentially stoichiometry. And what I'm going to tell you is that if you can follow the units, if you can cancel units throughout a problem, you can solve these problems. If you struggle with units, I would highly, highly, highly recommend making sure that you are labeling everything in your problem so that you can cancel out those units. All right, so this says how much charge passes through the cross-section of a wire that is carrying 0.987 A, that's amps, of current for 12.3 minutes. So again, when we see this A, what I need you to think, amps is equal to coulombs per second. So we're going to think of this as 0.987 coulombs over 1 second, and that's going to help us to solve this problem. We're going to start with minutes, because that's something that that's a given that is not going to be used as a conversion factor, because this is 12.3 minutes. So for letter A, we're going to start with 12.3 minutes. And what I can see from what the information I have in my problem is that my amps is coulombs per second. So I need to change these minutes into seconds. So for every 1 minute, there are 60 seconds. And now I am trying to figure out charge. Charge is coulombs, so I want to get to coulombs, which if we look at what we've written down so far, this is coulombs right here. This is what we're trying to find, C. So that means I want that on the top so that I don't cancel it out. So I'm going to have 0.987 coulombs per 1 second. Now double check your units, make sure everything cancels. Minutes, seconds, and we're left with coulombs, which is charge. Sig figs would come from here, you're given, or here, because that's a given quantity in your problem. So both of those have 3 sig figs, so this would be 728 coulombs. The next question says, how many moles of electrons pass through the cross section? There is another slide on the next page that's blank if you want to write it there. I'm just going to write it here because I have some space and I don't want to have to come back to find the question. Okay, so how many moles of electrons passed through the cross section? This is where that Faraday's constant is going to come in, because there's 96,485 coulombs in 1 mole of electrons. And the question is asking about moles of electrons. So start with your 728 coulombs, and then we're going to use Faraday's constant to get to moles of electrons. 96485 coulombs. So now units, my coulombs cancel, and I'm left with moles of electrons. So this is 7.55 times 10 to the minus third moles of electrons. Okay, last page. So I skipped a slide because I wrote it on the last slide. But metal refinement and electrolysis. Metals can be refined through electrolysis. So I can plate out or get solids of other metals by doing something like passing a electric charge through it. So solid copper is plated out on the cathode of an electrolytic cell through the following process. So if I have Cu2 plus in solution and I have some Br minus in solution, I can then make solid copper and Br2 as a liquid. And then there's calculations that we can do, which we're going to walk through some like that in a little bit, that is going to talk to us about how much of that solid we can make, or how many moles of electrons did we transfer and stuff like that. So the next 4 problems kind of go along with that. I guess there's 3 problems, but the next 4 slides. Oh, why is this not working? There we go. Okay. So again, make sure you're thinking about canceling out your units. Follow the stoichiometry. So how long? We're looking for time. That's what that how long part means. Would it take to plate out 3.56 grams of silver from a solution containing Ag plus ions? We have Ag plus ions in solution when a current of 2.5 amps is applied. So again, we see that amps. What should we be thinking? Coulombs per second. Okay, amps, every time you see amps, think coulombs per second. So how long is what we're looking for? We have a mass. Let's start there because that's the only other number that we have that can't be used as a conversion factor. It doesn't have a unit on the top and a unit on the bottom. So 3.56 grams of silver. And then eventually we're going to use like Faraday's constant, which is going to talk about moles of electrons. So we need to change this grams of silver into moles using the molar mass. So 107.87 grams of silver in 1 mole of silver. Now, the next part that we can think about with silver is how many moles of electrons are transferred from Ag plus to solid Ag. Since it's a plus 1, that means that for every 1 mole of Ag, 1 mole of electrons has been transferred. Let's cancel our units and make sure we're doing okay so far. Grams cancel, moles cancel. We're left with moles of electrons. So now think about what else do we know about moles of electrons? What other conversion factor might we use that has moles of electrons? We just talked about Faraday's constant. Faraday's constant says that there are 96,485 coulombs for every 1 mole of electrons. See how my units are canceling there. And then I'm into amps. Or then I have my amps, which is coulombs per second. I have coulombs right now that I haven't canceled out yet in my problem. So I need to use that to figure out my time. So I want coulombs on the bottom. So this is 2.5 coulombs on the bottom for every 1 second on the top. It doesn't say seconds or minutes. I'm going to go to minutes just because that's what I wrote down earlier, and that's the answer that I have. But if you kept it in seconds, there would be absolutely nothing wrong with that, because it did not specify what unit of time we needed to be in. So then do your math. Multiply across the top, divide by whatever you have on the bottom. Sig figs would be 2, because of this 2.5 amps. So that's 21 minutes is how long it would take. Okay, Let's look at another one. Okay. This one says if 2.0 Faradays of electric charge pass through a silver nitrate solution, what mass of silver is plated out? So this is going in the opposite direction. So 2.0 Faradays. A Faraday is 2 Faradays is 2 of Faraday's constant. Okay, that many coulombs times 2. So we're going to start with that 2.0. And then we're going to times it by Faraday's number here, 96485 coulombs. What else do we know about coulombs? Well, Faraday's constant. For this many coulombs, we transfer a mole of electrons. So now think again about what we've got going on here. Silver nitrate is going to be an Ag+. And we're trying to make solid silver, which is an Ag. So that is 1 mole of electrons for every 1 mole of Ag. And then from there, we know how to get to grams. Again, cancel your units, follow your units. Sig fig wise, we're going to go with 2. This is the only number that was given to us in the problem. So this is 220 grams of Ag. All right, one more problem that has 2 parts, and then we are done. Okay, this one says 1.40 grams of an unknown metal with a molar mass of 150.0 grams per mole was plated out on the cathode after applying 0.500 amps of current for 60 minutes. Again, we see that A, we see that amps. Please think coulombs per second. What is the charge of the unknown cation? So we're trying to figure out, is it a +1, is it a +2, is it a +3? How many moles of electrons per 1 mole of stuff has it lost, basically? All right, so first it tells us to find the moles of the unknown metal. This is a simple grams to moles problem. So 140 grams of our substance multiplied by its molar mass. Grams on the bottom, 1 mole on the top. This is going to be 0.00933 moles. Okay, that's our first step. Our second step is to figure out how many moles of electrons were transferred. Well, we have the amps and we have the amount of time it took. So we're going to start with time, again, because that one doesn't have a unit on the top and a unit on the bottom. It's just one thing. So we've got 60 minutes. We are going to change that into seconds because our amps is coulombs per second. So there's 60 seconds in a minute. Then we're going to use that current, or how many amps it was. 0.500 coulombs per second. And then what do you know about coulombs and moles of electrons? For every 1 mole of electrons, there are 96,485 coulombs. That's going to give you your moles of electrons that were transferred, which is 0.0187 moles of electrons. So now the last part, to find the charge, we're going to find moles of electrons per moles of metal. So your moles of electrons was that answer we just found in the second step, 0.0187 moles of electrons, and then you divide that by your moles of metal, which was on the last slide, 0.00933 moles of the metal. And that comes out to be 2. So that means 2 moles of electrons per 1 mole of metal. So that means that it's lost, the cation lost 2 electrons. So it has a +2 or a 2+ charge. All right, you guys, that is it. That is everything that we have to cover. So make sure that you know the worksheet that goes along with this. We will check probably a day or 2 after we come back from break. But we are good on content, and I will see you after spring break.